All right. Hello, everyone. I am Professor Caudill, and we are going to do something a little different today. So we've got a timer going. So as you can see, I am Professor Caudill, and we are going to get started with computers and programs. One thing I learned from doing a little bit of deep learning is great at finding patterns. It's like a new way of programming where um, you, you put in, you give it examples and then it learns from the examples. So deep learning is good at predicting. The thing about it is if you wanted to make something that does something with that, so let's say like maybe you have a car, so and it has cameras on it, so it's collecting photons. So it's learning from the environment. But to actually do something, you have to program it. So the like deep learning um, model. So if you have a deep learning model, you have to, if you want to make something cool, you're going to integrate that in a bigger program. For example, you want something that, like, if you can predict where cars are going, that's nice, but you need those predictions inside of a program so the program can react. So if you're making an intelligent system, not enough just to know deep learning and AI. That's just like that's like a very small subset of the problem. So, and I'm not even sure how much we can we will program anymore with how popular AI or large language models are getting. It's like, is it even worthwhile to learn programming today? I think there are good arguments not, but um, I do want to learn like more Python, especially with like Jupyter Notebook. I feel like there's a lot of cool things we can still do, especially with like microcontrollers. So I downloaded this textbook, John Zell, third edition. I think I found it off of art somewhere online. Somewhere online you can get this. So we're gonna take a shot. Here's the table of contents. Guido von Rosen, that guy, he is one of the founders of Python. So it's hard to keep up with the pace of technology. So I think understanding like this chapter one will be like I don't expect a lot of this content will go away. So I feel like this might be worth learning. As far as these are more questionable because yeah, they might be worth knowing, but there's also the argument that if we study these, then we are more able to prompt large language models to do what we want. So yeah, let's just get into it. I'm just more, this is kind of just exploratory as far as intelligent systems go. So yeah, just deep learning and AI is just one subset of the whole problem. I'm also hoping that there's no issues with recording. Um, so I know I'm on a new Linux distro. This is Pop OS. So I know on Ubuntu Mint sometimes OBS would crash or one of the displays would stop working. So I have some anxiety, maybe like middle of this recording, something goes wrong, but I hope nothing goes wrong. So let's just get into it. Computers and programs. So can I make this a little bigger? Okay, this should be good. Okay, great. So chapter 1, computer programs. So we want to understand the respective roles of hardware and software. So what's scientists study? Basic design of a modern computer. For example, can one make an operating system with the LLM, large language model at the lowest level? So basically, when you start up a computer, instead of can we replace the BIOS with a large language model? That's one thing I'm curious about. So we want to understand the form and function of computer programming languages. So Python is a high level, so you have, if you're thinking of software stack, you might have Python on the top. This is a high level, and then you might have C, C++, and then you get assembly, you get binary. So, and I'm curious if LMs are like the next layer on top of Python. Like, are large language models just another layer of programming languages? Where does AI fit in that? So Python. So Python, what do? You're in contra to AI. You're not giving it inputs. You're specifically or you're yeah. So let me just say transfer deep learning, transfer deep learning slash AI neural networks are a different type of programming. I've heard that claim. So I'm not sure how this fits. Is there two types of programming? We have AI, um, with stochastic gradient descent, deep learning. So this is two ways of programming. Maybe we could call one discrete, where you're manually changing things, and then it's continuous, or we could call it dynamic, static programming. Types of program. Types of programming. So from what I understand, there's like static programming where you're manually you understand a process and you're manipulating you can manipulate parts of it to get a desired outcome. As far as AI goes, that type of programming is dynamic, where you don't really know the structure of the process, but you are just giving it examples, and you're changing to get, I mean, you're both in both types of programming, you're changing variables, and the user is changing variables, but it's more automatic in AI, and it's more like static. That's just like coming into this textbook. That's the mental baggage I'm carrying with me. Okay, so chaotic models, that's like chaos theory. Implementations for computing. So chaos theory, you're going to have vector fields. So you're going to see something like this, a bunch of straight arrows. And as you can see, this is not a linear function. And if this, like in this graph, could change here, so if you had a function that changes like this, you're going to get different features based on where variables are. Okay, so if you're over here, maybe the light switch is turned on. But if you're over here, maybe the light switch is turned on. It's turned on the left, it's turned on the right, it's turned off. Maybe in the middle, it's kind of halfway. Maybe it's like half dim, or maybe it is on here. Or maybe you have two light bulbs, so maybe both are on, and this is both off. And then maybe in the middle you have one off, one on, depending on where you're at in the loop. So this is chaos. That studies it's like the opposite of linear algebra. It's where you're studying like equilibriums and stuff, steady states. Computers are used to predict the weather. Computers are used to predict things. So computers predict things. So computers predict. Computers predict. So that seems to be true no matter what programming language So this is true regardless of language or this is regardless of your language or method. Okay, so yeah, so computers predict no matter if you're doing static or dynamic programming. What is static or dynamic programming? That's so if you're doing static, you're doing Python, C++, assembly, binary, maybe large language models. LLM's kind of in the middle here, I would say. LLM. So we're kind of in a gray area where the two types of programming are kind of merging. So AI, stochastic gradient descent, deep learning, that's like your dynamic programming. Hope I'm not like, hope my use of words isn't offending anybody. I know dynamic programming has like a technical definition. I'm kind of using it somewhat loosely here. Uh, like I know some people think dynamic programming involves like shortest paths, memoization. So have you ever stopped to wonder what exactly a computer is? Okay, so let me fix this. So we got some text here. Um, so a computer is a machine that stores and manipulates information. So a machine, let's draw a circle. Okay, so what's let's rewrite this machine. So if we have a set of machines, what might be in this set? We might have biologic organisms. We might have cellular automata machine. You might have, your cell phone, industrial robotics, um, desktop, let's just say PC. So biological organisms, that includes humans. I'm a big fan of drawing analogies between biology and artificial life. So you might be asking, how is a human a machine? So how humans are machines by this definition. So they store and manipulate information by so store so, store means there's two different perspectives from what I've read on the required reading from the deep learning previous lecture. So memory, some people view memory as like you put it in a hard drive. and you extract memory from like some kind of data set in the mind, in the brain. There's also competing theories where memory is not stored in some part of the brain, rather, memory is distributed and expressed as the in the it's expressed as how strong a synapse is, a synapse which connects two neurons. So if you have two neurons, we're going to say this is weight 1, two neurons, this is weight 2. Okay, so let's say the value, so let's say weight 1 is greater than weight 2. So therefore weight 2 is more likely to be remembered slash recalled. Okay, so now humans have a way of storing information. This is supposed to be a dot for short for manipulation, information. Info is short for information. So now we need to know, how do humans manipulate these? So maybe you could say habits alter the strength slash value of a weight. Okay, and we're going to say the n weights. You have like 10 to the 11 neurons in your brain, so we're going to say n, where n is an element of a 1 dot 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 to 10 to 11. Okay. Maybe that's not true because each neuron might be connected, so would that just be 2? Would that be 10 to the 11? 10 to the 22? 10 to 11 to the power 2, so maybe let's just say 10 to the 22. So 10 to the 11 individual neurons, if each one is connected to each other, would that be more or less synapses? I know there's an answer. I don't want to get stuck on it, so I'm going to move on. But you get my train of thought. So humans store and manipulate information by their neural circuitry and their habits. So and habits. Okay, so what else do they do? Under the control of a changeable program. So what is the program of humans? That is their habits. So for example, you can program habits via culture, societal pressures, like laws and maybe education. Um, what's right? Forced education, like K through 12, forced education. So as we see, a modern computer is can't like a human falls under the definition of a modern computer. Let's see. Computers are devices for manipulating information. Okay, so we're gonna say I wanna say humans are devices. That implies like there's a user, unless you're saying the individual self is a user, which is reasonable. So we can put information into a computer. So this might be termed like influence. Maybe you can influence a person. That's one way of putting information in them. Or you can just make them sit and watch a lecture or a presentation. So this is kind of what we're doing in this video. We're transforming information into new useful forms, and by uploading this video to YouTube, we're displaying the information for your interpretation. So everything I've said here, you can disagree or agree, or you don't even have to make a judgment. You're a free mind. So it is funny because some part of me had like this preconceived notion, like, okay, AI, it's like I can do anything with AI if I just learn it, but it's just one piece of engineering. It's like engineering is hard because it integrates so many disciplines and techniques and sub-disciplines and sub-techniques. So if we're trying to do useful things, um, I wonder if following textbooks is like the best strategy for the shortest path. Building cool things and life extension technology, that's one of the one of the high callings for me personally is life extension technology. So when you use a simple calculator to add up a column of numbers, you are entering information, numbers, and the calculator is processing the information to compute a running sum, which is then displayed. You fill up your tank, the pump uses certain inputs, the current price of gas per gallon, signals from the sensor that reads the rate of gas flowing into your car. The pump transforms this input into information about how much gas you took and how much money you owe. So if you're familiar with this with my channel, I like exploiting or just studying the differences of West, East philosophy, and one key idea from this is viewing man different from nature your Western or viewing man as one with nature. So this is important for computer engineering because I feel like you might be robbing yourself, or you might even be unethical if you are using the Western view, especially when you get into like artificial life and you continue using machines as tools designed or with the sole purpose of serving human masters. Uh, so I don't want to get too philosophical, and I know this book is probably going to be Western oriented. I just wanted to preface that that's like that's just one way of viewing of um, computer science. So gas pump, I would say that's more like a microcontroller or a SCADA. Um, they are different from computers in that they are built into form a single specific task. So we might call those ASICs, application specific integrated circuits. Okay. User continual program. So program is a detailed step-by-step instruction telling a computer what to do. So I'm curious how, if this definition matches that of like AI and deep learning. When you make a deep learning task, or when you tell a computer to, so if I order a computer differentiate um, pictures that can contain cats from those without cats. So if I want to program in Python, it's kind of it's like we're learning deep learning from a different approach. Like in theory, shouldn't you be able to do anything in deep learning with a with the traditional program? You should be able to do it. It's just like it would be like riding a horse to work instead of riding a car. It's just like a worse method, but like fundamentally, it should still be the same processes, I would think. So if we tell a computer to differentiate pictures that contain cats from those without cats, as we did in the previous videos, so then a computer program is our Jupyter notebook using fast.ai GitHub. Okay, so library. So we made a deep learning computer program using, let's say, the recipes from the Fast AI's GitHub. So, or we used tools from that GitHub. And those tools were instructions. So, instructions, yeah. So if we change the program, then the computer performs a different sequence of actions. So in theory, transfer posits one pre-trained model can be configured to do what? To differentiate objects besides just cats. So instead of so we give it a bunch of images and then I think we uploaded 7,000. So the pre-trained model was like 7 million images. And then we trained that model on 7,000 images of cats and dogs. I'm not sure. I'd have to like inspect the fast AI code to understand how they are selecting cats. Like how are they asking the algorithm to pick cats? That might be something we would need to look into. Okay, and likewise, this allows so it's also kind of this gets very philosophical as far as how one orients their life. Would you learn by following a step-by-step plan, or would you kind of look at a lot of examples and extrapolate patterns? For example, let's say Achilles is good at throwing spears, and I wanted to emulate Achilles. So let's say I change all my habits to be as close to Achilles' habits as possible. That's one version of computer programming. And a different way is, okay, maybe it's better to look at all objects like Achilles, all spear throwers, look at all examples of spear throwers and study them, and maybe through that study I detect patterns and layers, patterns from different types of um, complexity. So maybe by understanding different orders of patterns, then maybe I become a better spear thrower than Achilles himself. So this this is why this is so interesting to me, because the vision of programming methods, giving examples versus explicitly programming, is so opposite. It's just like the Western Eastern philosophy. There is so different ways of viewing the world, and if the mind is a computer, that completely changes how you live, how you learn. Um, so really, in a way, reading this textbook about Python programming, computer science, if you're really geeked out, you might just view it as like a guide on how to live. Um, I just want to check because I am doing some different things, so I want to make sure that everything, all the formatting with the new recorder and operating system are working. Okay, so everything's working. So the machine stays the same, but the program controlling machine stays, but the program controlling this machine changes. Okay, so I could rephrase this as the body stays the same, but the mind controlling the body changes. So every computer is just a machine. Every computer is just a machine for executing programs. The body. So let's say the body with, I say, a mind embodied entity. Mind and body entity is about, it's like a computer. So the mind can change, but when you put the mind that changes inside a body, then that's a computer. Maybe. Again, I'm kind of thinking out loud here. I'm not saying you should think this way. Just think for yourself. Um, each computer can do basically the same thing other computers can do. So what this means is anything that AI can do, a human can do. Anything a human can do, an AI can do. Okay, so this is just fundamental um, computer science. And if that makes you uncomfortable, it's probably because you have a strong Western background with philosophies from like Judeo-Christian, Amity, and pre-Socratics, um, separating the world into subject, object, predicate, sub subject object, um, subject predicate, chopping the world up into objects and classifications. But like the Eastern view would say like check those divisions, you miss out. You know, the Western view does not ask what is lost when they chop up and classify things. You know, when um, the act of chopping up is like severing. You know, like if I cut off my arm, the Western view might not ask about that functionality, or it might ask about it when it's too late. So that's why I feel like Eastern philosophy is in some ways more ethical than Western, because the Eastern view will ask what gets lost if you chop something up. But also when you're in defense of Westernism or Western philosophy, when you if you're just thinking, if you're just really thinking, you might divide and classify ideas and objects like carelessly, and uh, you might not have bad intentions when you do that. So PC is a is really a virtual a universal machine. It can do anything you want it to do, provided it can describe the task to be accomplished in sufficient detail. So, the thing about the Fast AI textbook is I didn't find that it described the task in sufficient detail. Okay, so the Fast AI textbook, chapter 1, what did they say? They say use our GitHub, use our library instructions, run those instructions on cloud GPUs, and now you are a deep learning engineer. I know the authors probably disagree with this, but that's like my first impression of the Fast AI textbook. So I don't really know how to make an AI or deep learning model. I know kind of some of the technical terms. I know I've seen some of the graphs on how it's designed. I know that like the weights these days get automatically changed. So really the only thing that you're programming is you're just changing the error rate. So by manipulating error rate and data set that it's trained on. So that's the only thing the programmer is changing is the error rate, like your error rate or whatever affects the error rate. Okay, so you program by manipulating what affects the error rate and data set of your model. So it, I think the textbook is saying this is sufficient detail to do AI. Um, Find a GitHub, run programs you don't understand. Um, Running I'll just go ahead and say running programs one doesn't understand is bad cybersecurity. I didn't inspect the fast AI source code. Maybe this textbook would help me identify malicious code, but there's some like level of trust in the open source community. It's kind of like blind faith, like it's open source, so everyone can view the source code, but the person using the code kind of presumes that someone else has already inspected it, therefore it's safe. That's kind of like one of the flaws of open source community is um, kind of believe in like an invisible inspector that might not be there. Um, so yeah, Fast AI textbook, use their library's instructions, run those instructions on cloud GPUs. Now you're a deep learning engineer. They say program by manipulating what affects error rate and changing what data set is used to pre-train the model. So I would argue running programs one doesn't understand is bad cybersecurity. Also, I don't really feel like I understand deep learning that much. I understand enough to know that deep learning in itself is only one part of the entire engineering. Like you need, for example, if I wanted to make a program that stopped my video game character from dying, so if I had a deep learning model that predicted actions that resulted in death, the FastAI textbook says that's all it can do is predict. If you wanted to act on those predictions, you have to build a computer program that takes the predictions. So we have to build a program that takes deep learning predictions. And so the issue with this is also the compute. Um, it's like think of it as like the most expensive video game cheat in the world because you would need like a Tesla A100 GPU to have a program that's predicting when your character is going to die, and that prediction is input and becomes real time input for a um, mouse, keyboard, action, or let's say script. Say script. A script is like a macro. It's like it does actions. It can do like 3 actions in one, or it can click 3 spots with 1 click. For example, So if I wanted to build a program that takes deep learning predictions and uses those as real-time input for a mouse or keyboard script to stop video game from dying. So as you can see, it's not enough. It's not enough to have something that classifies cats from dogs, or in this case, life from death. If I have a model that classifies life from death in the video game, it has to continuously read the state. It has to continuously be monitoring my monitor. So when I prompt the model with an image and I ask it, is this a cat? That takes several seconds, like 9 seconds, for example. In a video game, that's too long. I need a language model that can answer prompts at milliseconds, at approximately 100 milliseconds. I think that's about the time neurons travel through the nervous system. It's about 100 milliseconds on average. I think it's faster if you're just in the skull. It's about 1 to 10 milliseconds in the skull, but if you're going down the spine, it's about 100 milliseconds. So I think that's one of the errors, one of the flaws with today's AI, is it models itself after neural networks, but the runtime is not like I can't do that for cheap. And I think cheap compute is like an argument to be made in computer science. If it's not cheap to compute, it's not worth computing. Therefore, it's useless. So, where are we at with the timer? 52 minutes left. So we are on. That's a powerful machine. Okay, so next video, we'll get into that. I'm kind of impressed that I spent a whole hour on just this section. Hope you guys don't mind. So yeah, we'll end the video there. And I hope you guys found value in this video. And give me a like if you like this new format for the video. All right, I will see you later. Goodbye.